Let us consider delta PL2 as a change in load in area 2. We get the following relationships by considering the energy balance situation at area 1, which is delta PM1 minus delta P12 exchange of power among the corporations is equal to change in frequency delta omega into D1. Therefore, this equation is written from this perspective. Delta PM1, delta PL1, delta P12 and delta omega 1 and D, where delta PL1 is 0, only delta PM1, delta P12 and delta omega and D1 were interconnected in this continuation that you can see here. Infinitesimally a small change in demand on tie line power and a mechanical change in power at area number 1 where there is no change in load in area 1 reflective as change in frequency as delta omega with the frequency sensitive loads at that area defined by D1. Similarly, when there is a load in area 2, change in load in area 2, now we can write similar equation concerned to area 2. What is that? Here, add this summer block. Delta PM2 plus delta P12 minus delta PL2 of S. Demand in area 2, reflect it as delta omega 2 into D1. That is the equation what we can write here. Delta PM2, the infinitesimally small change in power at area 2 plus the power received from area 1 towards the area 2 and a load change in area 2, which reflective as delta omega into D2. This is delta omega because delta omega 1 is same as delta omega 2. It is referred commonly as delta omega. Now, from these two equations, we can rewrite what is delta P12 using delta PM1 from the governor characteristics. We know that delta PM1 can be written from the observation in the previous slide what we have seen. Minus delta omega by R1 and delta PM2 is minus delta omega by R2. By incorporating these things over here, we can rearrange this equation as minus delta P12 is equal to delta omega inside the bracket D1 and 1 by R1 from this term getting taken into other side. You can see here delta omega D1 plus 1 by R1 becomes revised equation number 1. Similarly, I can write delta P12 from this particular second equation perspective. What is delta P12 minus delta PL2, which is delta PM2 on replacement by minus delta omega by R2. I can transfer it to the RHS side. I can rewrite it as delta omega outside D2 plus 1 by R2. Therefore, I have revised minus delta P12 and delta P12 minus PL2. By using these two, what I can write? I can rewrite these equations such that delta omega can be taken out. So delta omega nothing but frequency deviation noticed in an area 2 is given as the value. From this perspective, when I replace, I will be getting it as minus delta PL2 minus delta PL2 divided by beta 1 plus beta 2, where we have already discussed beta 1, beta 2 are the composite frequency responses from area 1, area 2. So therefore, we should be very careful about that. So this is obtained. How we have obtained this, you might be wondering. You can use this delta P12 in this position. Then this delta omega 1 plus D1 plus 1 by R1 in this position. When I transfer respectively to other side, it becomes additive. Along with which delta omega is common, I can replace this as a beta 2, this as a beta 1. Therefore, minus delta PL2 divided by beta 1, beta 2 stand as delta omega. This is what the simplification from this equation can be brought. Similarly, this is about the deviation what we find when there is a load change in area 2. How about the power being exchanged among the corporations 1 and 2? That is called delta P12, which is again taking the equation, we can rewrite it. So delta P12 can be rewritten as delta PL2, change in load in respective area, which is 2, into opposite area frequency response composite divided by the response composites 1 and 2 added in the denominator, which stand very similar as minus delta P21. It means delta P12 power flowing from 1 to 2 is exactly opposite to power flowing from 2 towards 1. Hence we have one negative sign over here. So therefore this is the representation. The power flow from 1 to 2 for a change in load in area 2 is step change in area's load into opposite areas composite frequency representation response divided by sum of the composite frequency responses in the denominator. This stands as one of the important equation. So how you got it, you might wonder. Again, from substitution of these things in the respective equation, I can obtain this. So therefore, we can definitely get these things in line with the requirement. Or else, very simple, we can just consider these things in the respective substitution back and we can get back. So this is about change in area to how the power flow occur and what is the deviation noticed in that area. Suppose there occur a change in both the areas. We can quantify it further having considered delta PL1 a change in load, delta PL2 a change in load in respective area, and delta P12 as power exchange among the corporations. This we can take as separate case study considering load change in both the areas. Before going to do this, let us consider few examples how is that change in load of area 2 is addressed in numerical problems. Let us move to some numerical problems. So considering the two areas with the generator as mentioned, we have R1 D1, R2 D2 on a certain base of 500. A load change of 100 megawatt occur in area 1. How we can find out the steady state frequency and new Thailand flow using the respective equation using area 1 load change perspective we have done, which is change in load divided by beta 1 beta 2, which quantifies delta omega. As the load change is incremental, definitely frequency falls. Taking the base frequency of 60, drop to the particular 0.001318 pu, converting it to hertz, it leads to 59.92 hertz. Then change in Thailand power flow. Power flowing on Thailand due to the change in load in area 1 can be quantified as delta omega into beta 2. Beta 2 stand here as 1 by R2 plus D2. On substitution, we get 33.6 megawatt flow here. Very simple problem using the equations. Let us move to next one. What is that change in power worked out at area 1 at area 2? Because it's only primary loop based control, both the area will respond for that. So this if we consider minus delta omega by R1 stand as 0.1318 into 500 if I do, it becomes 65.88 megawatt is the change in delivery from mechanical aspects of area 1. Then in change in mechanical aspects of area 2 for the change in load as minus delta omega by R2, which works out as 0.0659 pu, or into 500 if I do, it becomes 32.94 megawatt. Therefore, we should be very careful about the change in megawatts of respective area due to a change in any one of the area is to be worked out in single area concept or in a primary loop based concept. So the further interaction with respect to load were out of our reach. Let us ignore them because that is not the scope for the particular problem. Let us take one more new problem which you can identify. Two control areas of capacity 1500 megawatt and 10,000 megawatt are interconnected through a tie line. The parameters of each area on its own capacity are the droop R equal to 1 hertz per pu megawatt and D 0.02 pu megawatt per hertz. There is no increase. There is an increase of load by 200 megawatt in area 2. Determine the steady state frequency, deviation and change in tie line power flow. This problem fits to area 2 load change. Let's take the values 1500 megawatt and 10,000 megawatt, and droop and frequency sensitiveness of the area is given, R and D common. We have to reflect them on one of the area with the base and another with the shifted base. Let us consider all these to a common base 10,000, because load changes at area 2 is a quite comfortable view to do it. In case of main examination, if so, common base must be specified and common frequency must be specified. In this, let us consider the common base as 10,000 megawatt and base frequency as 50 hertz. Let us convert all these R and D to R1 D1 and R2 D2 respectively using these new values of base what we have to convert. Therefore, R1 nothing but droop of machine 1 area is 1 into 10,000 divided by 1500. We are converting that hertz per PU. That PU is on the base of 1500 in area 1, but I want to get it shifted to 10,000 megawatt scale. Therefore, 1 into new base divided by old base. That stand as 6.667 hertz per PU megawatt. Similarly, D1, the D is given as a 0.02 PU megawatt per hertz. I want to shift it to new base of 10,000. Then it is opposite, 0.02 into on which it is working 1500 divided by new base. When I do, it become 0.003 PU megawatt per hertz. So I got R1 D1 converted to 10,000 megawatt base. How about R2 D2? R2 D2 are to be considered in a very simpler manner like this. Let's see what is beta 1. I can write beta 1 is 1 by R1 plus D1, which I add them. 1 by 0.6667 plus 0.003 stand as 0.153 PU megawatt per hertz, because I can take them. When I take 1 by R1, units become PU megawatt per hertz. I can add them. That is an addition here, 0.153 PU. Similarly, beta 2. So beta 2, these values are directly referred on 10,000 megawatt. Therefore, I will be taking 1 by 1 plus 0.02 as 1.02 PU megawatt per hertz. So beta 2 is straightforward because values mentioned were on 10,000 base itself. Then what is that change in load in area 2? 200 megawatt. The 200 megawatt divided by 10,000 refers to 0.02 PU shift in load. So therefore, now I am in a position to get what is change in frequency, delta F. Delta F stand as here as minus delta PL2, change in load divided by beta 1 plus beta 2 from respect to areas, which if I substitute minus 0.02 over 0.153 plus 1.02 stand as minus 0.017 hertz. These values are in PU megawatt and hertz. Hence, this deviation I will get in hertz only. And you are very sure negative, because this increase in load definitely cause fall in frequency. So that is how this is minus 0.017. Then what is that new steady state frequency then? So I said very clearly in the beginning, if 50 hertz is the base frequency, then 50 minus 0.017 stand here as 49.983 hertz as revised frequency. Then what is that power exchanged among these two areas? Definitely, when area 2 is suffering, area 2 as well as area 1 has to respond because of primary loop. Therefore, delta P12 stand here as delta PL2, whatever is that shift in load, into opposite area composite response beta 1 divided by beta 1 plus beta 2. You can just see 0.02 into 0.153 over 0.153 plus 1.02, which stand as 26.08 megawatt. What was the load change actually? 200 megawatt. Then what is that contribution from the area 1 coming towards area 2? only 26.08 megawatt. Then what about remaining power? It must be a composition of change in share of area 1, area 2 respectively. This is what we can get. The change in delivery on tie line stand as 26.08 megawatt only. Let's say another important aspect, two generating areas have capacities 500 and 1000 megawatt respectively. They are interconnected by a short line. The percentage speed regulations from no load to full load of the two stations are 3% and 4% respectively. If the load on each station is 250 megawatt, find the power generation of each station and the tie line power flow. This is a very straightforward, simple ratio-based problem. Let us understand. Total load here is 500. Each station was sharing 250, hence total load is 500. The droop of first machine is on percentage. How to get it in hertz per megawatt? Convert it. 0.03 into 50 divided by 500. 50 stand here frequency, 500 stand here as megawatt. 0.03 into 50 divided by 500 stand here as 0.003 hertz per megawatt. Similarly, the second one is 0.04 into 50 divided by 1000. That stand as 0.002 hertz per megawatt. And we know that the share of total 500 megawatt should be from generating station 1 and 2. Hence, PG1 plus PG2 should stand as 500 megawatt as well. The droop of station 1 or generator 1, which is given by delta F by Pg1, and droop of second can be given as delta F by Pg2. Minus is taken out here. When I take these in proportion, what this delta F equal to? R1 into Pg1 is delta F, as well R2 into Pg2 is delta F. If I equate them, what I am going to get? R1 Pg1 is equal to R2 Pg2. Using this relation, Pg1 and Pg2 I know total equal to 500, and one of them if I substitute in the other, I can get single equation to get the share of Pg1 Pg2. Therefore, if I substitute it, R1 Pg1 0.03 Pg1 equal to R2 0.002 into 500 minus Pg1, I will get Pg1 as 200 megawatt. Similarly, 500 minus 200 stand as 300 megawatt. So this way I will be able to get area 1's share 200 megawatt, area 2's share as 300 megawatt. So this is how we can get the calculations. Very straightforward. It is just ratio based problem. Let us make one more problem. Let us search area 2 load alone. It will be easier for us to work it out. Let us use this only. Two areas, area 1 and area 2 are interconnected. The capacity of area 1 is 1500 megawatt and area 2 is 500 megawatt. The incremental regulation and damping torque coefficient for each area on its own base are 0.02 pu and 0.9 pu. It is R and D given respectively. Find the steady state frequency and change in steady state tie line power for an increase of 60 megawatt in area 1. The nominal frequency is 50 hertz. Therefore, you have been given droop and frequency sensitiveness on PU basis and the nominal frequency as 60 hertz. There is an increase of 60 megawatt load in area 1. So we need to take care converting them on PU and shifting back to megawatt works comfortable here. Therefore, the first let us convert the R2 and D2 to respective bases. So we have the R2 D2 on the base of area 1, which is 0.2 into 1500 divided by 500, which stand here as 0.6 pu, and D2 stand here as 0.9 into 500 divided by 1500 as 0.3 pu. So we got R2 D2 on pu basis with respect to area 1. Note that the unit R2 is in hertz per pu megawatt, while that of D2 is megawatt per pu hertz. So you should be very careful about these units. And change in load is 60 megawatt, which is 60 divided by 1500 stand as 0.04 pu. Then the deviation in frequency can be given as delta omega or delta f equal to minus delta PL1 shift in load in area, which is 1 in this case, divided by beta 1 plus beta 2, which if I substitute 0.04 minus divided by 1 by 0.2 plus 0.9 plus 1 by 0.6 plus 0.3 respectively, R1 by R1 plus D1 and 1 by R2 plus D2, which stand as a frequency deviation of minus 5.0847 10 to the power minus 3 per unit. And I said 50 hertz is the nominal frequency. When I multiply with the 50, I'll be getting 0.2542 hertz drop. It's called minus 0.2542 hertz is the deviation. So I can get new frequency as what? 50 minus 0.2542 as resultant frequency. For me, tie line power change is another requirement, which is delta P12 equal to minus delta PL1 into opposite area composite frequency response beta 2 divided by beta 1 plus beta 2. So it was very similar when we wanted to work with the change in power with respect to area 2's load. We had change in load as delta PL2 and beta 1 divided by beta 1 plus beta 2. So there is a small change in the numerator that has to be taken care depending upon the load change in the respective area. Rest is just substitute in the respective position and get the numerical content of that. So it is minus 0.04 into 1.9667. What is this 1.9667? It is beta 2, which is 1 by 0.6 plus 0.3 divided by similarly beta 1, beta 2. When I position, I will be getting total value as 5.9 plus 1.9667. When I take this relation into simplified steps, it stands as minus 0.01 pu, and to get the real megawatt, multiply it by 1500. 0.01 into 1500 as minus 15 megawatt. So therefore, there is a 15 megawatt flow from area 2 towards area 1 in this context. The load change is 60 megawatt. There is no doubt about it. So change is 60 megawatt, but power contributed from the area 2 is 15 megawatt. What about remaining power? 45 megawatt has to be taken care in the area 1 itself. Now this is to elevate you. The primary controller alone will trigger both the areas to respond. We want to understand this and we want to find a solution for this. If area 1 is suffering, area 1 should work for that. Area 2 is suffering, area 2 should work for. Then it is called later tie line bias control. So this problem highlight you so that both the areas are responding for the change in load like that. Similarly, we have number of problems possible in this respective. So therefore, in the next class, we will again see what is that interconnected area when both the areas are suffering, how the changes will come into picture. Let's say change in load in both the areas. When I have a change in load in both the areas, respect to energy balance equations, I can write from the block diagram. Equation 1 stand here. The summer block of the area control loop here. What is this energy balance? PM1 minus delta PL1 minus delta P12 equal to delta omega into D1. That's the energy balance equation I am speaking about. You can see. When both the areas are suffering a change in load, delta PL1 is in area 1, delta PL2 is in area 2, which I can say minus delta PM1 minus delta P12 minus delta PL1 equal to delta omega into D1. Similarly, other equation delta PM2 plus delta P12 minus delta PL2 equal to delta omega D2. Now you will find exchange of power among the corporations and there is a change in load in area 1. This is a demand on area 1. This is a demand on area 2. Both the areas are experiencing a change in load. Then the delta omega are commonly felt by both the areas. How is that? Energy balance is worked out. So therefore, it's the same thing again. Take the equation number 1, minus delta P12 minus delta PL1. Using this, I can simplify the equation. How I'll be doing? Delta PL1 minus delta PL1 and minus delta P12. I hold here only. Delta PM1 using the minus delta omega by R1, I transfer to the right hand side. Similarly, in this equation, what I will do? I will just do delta omega minus divided by R2 over here and I transfer it to other side. And later I rearrange this equation using what is that? Addition of these two. If I add these two, there is a cancellation of delta PL, P12, P12 over here. What remain here to me? I have to work out. Let's see here. Minus delta PL1 minus delta PL2. When I take these two addition, minus delta PL1 minus delta PL2 and these two cancel. This term I transfer other side. This term I transfer other side as a 1 by R1, 1 by R2 respectively with the delta omega. You can see here. My delta omega D1 minus PM1 plus delta omega D2 minus PM2. We know that PM1, PM2 are minus delta omega 1 by R1. I can shift it 1 by R1, 1 by R2. When I take delta omega outside, what it happens? Delta omega outside, beta 1 plus beta 2, where beta 1, beta 2 are the composite frequency responses of area 1, area 2. Therefore, now we are in a very clear position to write change in frequency deviation when both the areas are suffering is given as delta omega equal to minus delta PL1 minus delta PL2 divided by beta 1 plus beta 2. Or I can take out minus out, load change in area 1, load change in area 2 divided by composite frequency responses of area 1, area 2. I have to write. This way we can write the deviation experienced by both the areas when both the areas are simultaneously suffering for the change in load. From the above equation, frequency deviation, which is the equation, we get what is that? Exchange of power among them. Yes, look into this. Delta PM1 plus delta P12 minus delta PL2 equal to delta omega 2. That is for second equation I have picked here. From this, on substitution of delta omega from this, I can rearrange what is exactly delta P12. Delta P12 is, we can see here, minus delta PL1 beta 2 divided by beta 1 plus beta 2. What is this exactly? When I study a single case study, load change in area 1, this was the power flow from area 2 towards 1. Delta PL1 is the change in load in area 1. Beta 2 is the opposite area frequency composite response divided by sum of them. So therefore, this is first term responding as if area 1 experiencing a load change. This was a reflection. Then second one is delta PL2, change in load in area 2 into opposite area composite frequency response, beta 1 divided by sum of the responses. So together respond, together represent me net exchange of power among the corporations. So therefore, it's very simple. Delta P12 among the corporation, whenever both the areas are experiencing a change in load, can be written in this way. So therefore, delta P12 is in the numerator minus delta PL1 beta 2 plus delta PL2 beta 1 divided by beta 1 plus beta 2. So these two equations, one is of frequency deviation delta omega, another is change in tie line power flow. We have to consider for the numerical problem. So this will be very useful derivation we need to consider. Let's take one numerical problem which both the areas are experiencing a change in load. Let us see. Can you see here? The area of data of two area system PG1, PG2, 1000 megawatt, 10,000 megawatt and 0.015 0.0015, D1 equal to 0, D2 equal to 0, like that. So this will not take because this is an ACE based problem. So we'll search another problem there. You can see here this problem. Two control areas having the following data: area 1 R1.1 pu, D1 0.8 pu, rated on 1500 megawatt MVA. Let us take this problem. Yeah. Two control areas have the following data. Area 1 is having R1 0.1 pu, D1 0.8 pu, rated on 1500 MVA. Area 2 is having 0.098 pu droop and 0.9 pu frequency sensitiveness with respect to loads and rated on 500 MVA. A case study is a load increase of 100 megawatt occur in area 1. Find the steady state frequency and tie line power flow change. And the load increase of 100 megawatt occur in both the areas. Find the steady state frequency and change in tie line power flow. Case number 2. Let us understand the first case study. When there is a need to convert the bases to common, we have to do it first. You can witness it. First machine is on 1500 base, second machine is on 500 base. Now it becomes very necessary to convert it into respective bases. Let us convert R2D2 to base 1. Base 1 is 1500. Converting 0.098 to 1500 means value into new base divided by old base. You can see here 0.098 into 1500 divided by 500 stand as 0.294 pu. Similarly, D2 is opposite, 0.9 into new old base divided by new base because it is opposite units. 500 divided by 1500 into 0.9 stand as 0.3 pu. So from this, I can definitely write beta 2. And beta 1 is direct because it is already on the base of 1500. So I can write beta 1 as 0.1 by 0.1 plus 0.8, which is equal to 10.8. Beta 2 is 1 by R2 plus D2 as 1 by 0.294 plus 0.3 as 3.701. This is the prerequisite of getting beta 1, beta 2. Now, what is the load change in area 1? 100 megawatt. 100 divided by 1500 stand as 0.0667 pu. Case 1 we are studying. Therefore, frequency deviation observed is minus delta PL1 divided by beta 1 plus beta 2, which we can write it as 0.0667 divided by 10.8 plus 3.701. Numerically, we can find beta 1, beta 2 written in the above page we can utilize over here, which stand as minus 4.6 10 to the power minus 3 pu. So therefore, there is a drop in frequency as a load increased in area. And again, we have not been mentioned any frequency in the problem. So what we can consider in this problem, in line with the continuation of solution of problem, 50 hertz is the base frequency. Therefore, the frequency drop noticed in hertz is this value minus 4.6 into 10 to the power minus 3 into 50. That stand as minus 0.23 hertz. This is the drop in frequency from 50 hertz when a 100 megawatt load change occur in area 1. And also during which we get total frequency shifted down to 49.77 in this case. As well, net tie line power flow noticed is delta P12 from the area 2 towards area 1. The flow is minus delta PL1 into beta 2 over beta 1 plus beta 2. If I accumulate all this data in the respective places, I'll be getting minus 0.0667 into 3.701 divided by 10.8 plus 3.701. Very simple. What we have obtained, substitute them in the respective position and compute it as 0.0107 pu drop minus. Therefore, this if you convert it into megawatt, it stand as minus 0.01702 into 1500 as minus 25.5 megawatt. There must be a flow of power of 25.5 megawatt from the respective area. So this is how we can write the energy balance situation at that area as increase in load found 100 megawatt, increase in generation from area 1 perspective from mechanical objects which they are going to increase as delta PM1 equal to minus delta omega by R1. If I compute it, delta omega by R1 into a base of 1500, it stand here as 4.6 into 10 to the power minus 3 divided by 0.1 into 1500 as 69 megawatt. What we understand from this is for the 100 megawatt shift in load, the contribution taken by the area 1 alone is 69 megawatt. Then increase in generation of area 2, what is the share of area 2 is minus delta omega by R2, which we can write it as 4.6 into 10 to the power minus 3 divided by 0.294 into 1500, which stand here as 23.47. So we can see these two together make a noticeable difference. So therefore, this is how a share of load from area 1, area 2 for a shift of 100 megawatt is noticed in first case. The second case is the change in load of area 1 is due to the change in frequency. So there are frequency sensitive loads mentioned, which is with the D1. What is that change in frequency sensitive load? It is delta omega into D1. If I rewrite it, minus 4.6 into 10 to the power minus 3 into 0.8 on a base of 1500. That stand as 5.52 megawatt. There is a change in loads of that area which are sensitive to the frequency. There is a drop in frequency sensitive loads by 5.52 megawatt. That means we can just see here 69 megawatt is the share, 23.47 megawatt is the share. Together when I add, it won't become 100. Then what is that mismatch? Mismatch is due to reduction in inductive loads. That is what I am trying to calculate. In the first area, due to drop in frequency, 5.52 megawatt loads were rejected. As well, in area 2, delta omega into D2, when I operate like this, minus 4.6 10 to the power minus 3 into 0.3, which is D2 into 1500 as a base. 2.07 megawatt is the reduction in the loads. Together, they contribute 9 megawatt nearly. So, not 9, 7 megawatt nearly. So, we can just say change in generation is 92.4, 100 minus 5.52, 2.07 stand here as 92.4 megawatt. This is how the energy balance occur in area 1, area 2 with respect to drop in frequency, change in inductive loads. The case 2 is important for us because I wanted to show you when both the areas suffer change in load, how is that frequency deviation observed, how is that share of area 1, area 2 gets into reality. So therefore, delta F equal to minus outside the bracket delta PL1 plus delta PL2 stand as change in load in area 1, change in load in area 2. Respectively, you can say 100 megawatt change is the experience. So both the values are put in the numerator divided by composite frequency responses of area 1, area 2, beta 1 and beta 2. If I put them, what is that change in frequency deviation? 9.12 10 to the power minus 3 minus PU. This is so great change in frequency. Nothing but if I convert it to 50 hertz scale, it stand as 0.46 hertz drop. Very greater drop we are finding. So what is that revised frequency? 50 minus 0.46 is 49.54 hertz. The higher drop is noticed. Hence, the change in load of area 2 of 100 megawatt must be converted into base of 1500 and not on 500 megawatt because we are working on machine 1's area because everything we are converting towards area 1. This must be converted carefully. So therefore, tie line power flow change is minus delta PL1 beta 2 plus delta PL2 beta 1 divided by beta 1 plus beta 2. This was the standard equation we referred. Substitute the respective changes and get the value as 0.03265 pu. Nothing but 48.98 megawatt is the exchange power among them. Now therefore, we have to see this is the tie line power flow. What is that? Change in generation in area 1, change in generation in area 2, drop in loads of area 1, drop in loads of area 2. I have to account. To account that, let us go ahead in the similar manner, whatever the way we have done. So therefore, this problem convinces you how both the areas work together whenever they find themselves with a change in load. This problem also we can see a two area control system having area 1 with a parameter mentioned, area 2 parameter mentioned, a change of 100 megawatt load in area 1 and drop in frequency, nominal frequency, and repeat it for a change in area 2 also. Very simple. You can just see the problem how it is outlined. Hardly 4 to 5 lines of numerical substitution you need to follow very carefully. Please observe the problem on the screen and try to follow the steps which were already discussed similarly in other problems. Next, when the change is in area 2, how we summarize it? We have to be very careful about this. You can see the second half of that. Change in load area 1, how to summarize? Change in area load 2 due to frequency. When I summarize, how this comes into calculation. This part 2 is what? Suppose the change in load is in area 2 itself. How to address this? Similarly, we have the addressing mechanism. Delta omega I have to calculate. Change in frequency I have to calculate. There is a revised frequency. Then we have to work out what is that tie line power flow among the corporations. Delta PL2 beta 1 divided by beta 1 plus beta 2. That stand as 66.4 megawatt is exchanged among the corporations on the act of interconnected operation. This is how we need to work very, very carefully on that basis. Okay. So similarly, there are many more problems which are put to you for the study. Kindly go through those problems and you can understand. This problem is also one of the important problem. You have to just see the table and you have to follow the instruction given in the particular table and take the steps how it should be done. Look at the workout. So short workout which you need to follow. Hope you are able to perform these computations and able to achieve the requirements.